In 11.3 example 1, it asks us to use that expansion. And I want to again come back to what's on your formula sheet, that if you were given x plus y to the power of n, then term k plus 1 would be n choose k times x to the power of n minus k times y to the power of k. And I'd like to identify that in this example, we are going to take a look at the expansion. I'm going to write it underneath. If we have p plus q to the power of 6, then I can say that x is represented by p in that formula, y is taking the place of q, and n is equal to 6. And it's really important that what x, y, and n are, question by question, is not going to change. Within a question, x, y, and n are set by whatever binomial we're looking at. And some of them, x is just going to be x. Sometimes you're going to have x's represented by, I think, 2 a's in the second example, and along those lines. And the reason why I want to push this so much is that if we can identify that, x is represented by p and y is represented by q, then I can actually rewrite that formula and make it specific to this question. And I can say that term k plus 1 is equal to, well, n is 6. So it's 6 choose k times x, which is represented by p to the power of 6 minus k, times y, which is represented by q to the power of k. Now, the reason why this is so powerful is now what I can do to find, and another important idea before I forget, sorry about that, is the total number of terms is always n plus 1. So this particular question is 6 plus 1. We are going to have 7 total terms. And students really struggle a little bit with that. The reason we do is because the very first term, k is 0, and then we keep increasing k until it's equal to n. And really what that means is if I asked you to count to 6, you would probably just say 1, 2, 3, 4, 5, 6. But for the binomial expansion theorem, to get up to 6, we have to include 0. So we get 0, 1, 2, 3, 4, 5, 6, which is 7 numbers. So there's 7 terms. So what we're going to do in this expansion is we're going to use what I've written in blue, and we are going to write out the different terms. And I want to remind you that when I'm finding term 1, k is equal to 0. Because in that expansion, I'm going to say term 0 plus 1, which is term 1, is going to be equal to 6 choose 0 times p to the power of 6 minus 0 times q to the power of 0. And I'm going to write that out as 1p6 q0. I know we don't have to write q0, but I want to include it as we go, and I'm going to identify that's term 1. All right, now I'm going to keep going until I get term 7. So next up, we have term 1 plus 1, which is going to be equal to 6 choose 1 times p to the power of 6 minus 1 times q to the power of 1. That means that term 2 is going to be 6 p to the power of 5 q to the power of 1. And again, I know you don't have to write q to the power of 1, but I really think it's important as we go through these types of questions that we get used to the idea of some of the patterns that emerge as we kind of write maybe, more than we necessarily need to for a question like this. But it is a big advantage to see that the exponent on p is going down and the exponent on q is going up. But we got a little bit of work to do. I'm going to try to kind of spread my work out just a little bit now. I'm going to find term 3, which is when k is equal to 2. So term 2 plus 1 is going to be equal to 6 choose 2 times p to the power of 6 minus 2 times q to the power of 2. That means that term 3, if you put 6 choose 2 into your calculator, you get 15. We're going to have p to the power of 4 q squared. I'm going to try to do a couple in one line here. So I'm going to take term 3 plus 1, which is going to be equal to 6 choose 3 times p to the power of 6 minus 3 times q to the power of 3. If you put 6 choose 3 into your calculator, we'll get the term 4 is 20 times p cubed q cubed. All right, trying to get the last 3 in here. I'm going to get that term 5 is equal to, so in term 5, k is 4. So that's 6 choose 4 times p to the power of 6 minus 4 times q to the power of 4. If you put 6 choose 4 into your calculator, remember that 6 choose 4 is the same thing as 6 choose 6 minus 4, which is 6 choose 2. But if you put 6 choose 4 into your calculator, it gets you 15. So I'm going to say that term 5 is 15p squared q4. And now what I want to do, I know it's a little counterintuitive, but I want to write out all those terms. So I'm going to start from the very beginning. We can see term 1 just kind of what we said there. We have 1p6q0 plus term 2, which was 6 P5Q1 plus term 3, which was 15P4Q squared. And then we have term 4, which was 20P cubed Q cubed. Then term 5 is 15P squared Q to the 4. And what's really important about this is Pascal's triangle is symmetrical. And what that means is that if we picture splitting this in half, remember there's 7 terms, right? So this right here is what we would call the middle term. This expansion, at least the coefficient, is going to be equal on either side. So without doing any work, I know that this is going to be 6 for the coefficient, and the degree of P is going down by 1, so this is going to be P to the 1. The degree of Q is going up by 1, so that's going to be Q5. The last term is going to be 1, P0, Q6. And there's certainly a few different patterns emerging here. The most important is that the total number of terms is always 1 more than whatever n was, and the coefficients are determined by combinations. The degree of the x parameter is going down as we progress through, and the degree of the y parameter, in this case, P is for x, Q is for y, the degree of that Q is going up by 1. And you can see that in that expansion, that in term 1, it's P6, then P5, P4, P3, P2, P1, P0. Q is Q0, then 1, 2, 3, 4, 5, 6. And what makes this trickier is when both variables are the same. But if you have 2 different variables for x and y, you're going to see that pattern emerge every time.